Thank you. So, ROLIS is one of the imaging experiments on board the Philae lander on Rosetta. It is a compact camera. When we designed it 20 years ago, I would have said a miniature camera and a high-resolution sensor, but those two adjectives are not applicable anymore. Still, it is a very compact camera. It's about 10 centimeter in size. It is installed on the what we call the balcony of the lander, and it is downward looking. From this vantage position, the camera could operate during the descent and take images of the latest phase of the descent on the comet. And after the landing, it could acquire images in close-up mode. We have a bimodal optics. That is through a front lens, which is actuated by a motor, which is which can be moved in and out of the optical path, being focusing the camera at infinite during descent and the nominal distance of 30 centimeters after the landing. We have an illumination device of 4 arrays of a total of 144 LEDs in 4 channels, RGB and infrared, that is used to illuminate the field when we are in close-up mode. And we have a main electronics that also serves as interface to the Shiva imager. And it contains the memory buffer. So the operations of ROLIS are driven by the limited resources on the lander and by limited memory allocation. We don't know when the time of touchdown would happen. So in order to acquire the images at the highest resolution, we used a ring buffer where we store the images in several image in a buffer that contains 7 images, and the last image overrides the oldest one. At the time of touchdown, a signal is generated that stops the sequence, and then the latest 7 images are compressed and uploaded to the lander and then to the orbiter. I mean, now we know that we have been very lucky that all this worked, because once we received the touchdown signal and we rebalanced, we started nominally operating, compressing the images and uploading them, and we were lucky that the link was staying on all the time during bouncing. Otherwise, we wouldn't have gotten the images that we have. So after the landing, when in close-up mode, we would acquire 4 images in 4 colors. Through the rotation of the lander, we also have the possibility to acquire stereo. So this is the first image that was acquired. This was acquired at an altitude of 3 kilometers. The field of view of the camera is almost exactly 1 radian, so the field of view is 3 kilometers, and the pixel footprint is about 3 meters here. So the cross indicates the touchdown site number 1. So after this image, we went in ring buffer mode, and those are the 7 images taken at the maximum resolution that we have. They range from an altitude of 67 meters, where we have 7 centimeters per pixel, and the last image is at 9 meter altitude, and we have about 1 centimeter per pixel resolution. You see that during the landing, we have been turning with a rotation rate of about 0.6 degree per second, and the viewing direction was almost exactly nadir. We see that we are looking exactly at the center of the field as we progress. This is a mosaic, multi-resolution mosaic that contains all of the images. The central part has the highest resolution, about 1 centimeter per pixel, whereas the full image has a resolution of 7 per pixel. So the scale indicates about 10 meters. So we see that we have a leg of the landing gear on the upper right corner. So what we see is that we have a generally smooth and subdued terrain, which nevertheless is quite buried over the field of view of as small as a few tenths of meters. So the surface is dominated by gravel and blocks. This is really what we see. We have regions with different characteristics in terms of density of boulders and particles on the scale of 10 meters. So we see, for example, in this region that is labeled with a red color, that we see a region that resembles pits. We call it the pitty terrain. It is also characterized by a lesser frequency of blocks, and it is delimited by two terraces. So we believe that these pits are similar to pits that we see on other scales with Osiris, and those pits have a diameter of about 1 meter in size. One possibility for those pits is that they represent the feature caused by the collapse of the subsurface, for example, due to sublimation, or it could be also the result of an explosive event that then was filled up again. This is the appearance in close-up of this pitty terrain. So we also see features of possible downslope movement of boulders, although alternative explanations for this feature exist. We're analyzing now the orientation of the boulders to see whether this is compatible with rolling down of the boulders. We see some blocks that are buried. I mean, this block here, for example, the largest one is about 5 meters in diameter, and we're studying why this is the case. I mean, are those the effects of regolith mobilization? Are those outcrops that are being exposed right now? And we also see that the largest blocks have a particular feature that look like assemblages of smaller units, about 1 meter in size and having rounded shape. So is it what the largest blocks are made of? I mean, are we seeing basic units, and those units are later on being eroded? We also saw some clusters of blocks on the surface that hints at block fragmentation. And another important finding is that we see that even the very smooth terrains that are lower resolution appear to be completely smooth and like a cover of dust. At a higher resolution, they still appear to be granular. So we don't see dust deposits that are, even at our highest resolution of 1 centimeter per pixel, what we see is really granular material. So if dust is present, for sure we don't have many tens of centimeters of dust that blankets everything. So what we see is a structure at a centimeter side. So what we're doing now is that we are counting the particles. We want to determine the size distribution of these particles. We see different terrains, so we're doing this independently for different terrains. Our findings are preliminary. We still have to tune our procedures for counting the particles, but still it is interesting to see that in the size range, for example, between 20 centimeters and 4 meters, we have a power law trend which has a slope, a cumulative slope of about -3. And this is very interesting because, for example, with Osiris, we measured the size distribution of flying particles that are outbound and that are in the range of 2 centimeters and smaller, and they have exactly the same size distribution. So there appears to be a link. I mean, the particles we see on the ground are the same particles probably that we see flying outwards, and probably they're also falling back. I mean, they have the same size distribution. After the landing, we acquired images in different colors of the landing site. Those images are not processed; those are the raw images because the soil was at a slope. We have a very large difference in illumination in the field of view. So these differences first need to be calibrated out in order to see some content. And after we process the images, this is what we see. We believe we were not looking really downwards, but probably, as we saw from previous talk, the lander is landed on a side. So probably we're looking on a formation, a rock formation, or on a boulder formation, which is on a side. And we have a resolution of about 0.6 millimeters per pixel, and a field of view about 60 centimeters on a side. What is interesting is that we didn't find any individual grains opposite to the first landing site. Well, this is the second landing site, of course. And what we see are formations that are very, very similar to the ones that Shiva has seen. So we believe we're seeing the same kind of formation. And there is no sign of obvious color variegation. The color from the color ratios is very, very uniform. What we see is some degree of reflectance variation of about 4%, but very, very subtle, so no more than that. And everything is very neutral in color. So conclusions. So ROLIS managed to acquire the first close-up images of a cometary surface. The touchdown side, TD1, is covered by regoliths and blocks ranging in size from 5 meters down to the resolution limit of 1 centimeter. And we see signs of regolith mobilization and boulder fragmentation. We see what could be peaty terrain, and which can hint at subsurface sublimation or explosive events. We measure a size frequency distribution with the cumulative power slope of -3, which is similar to the one measured by Osiris in the outbound flying particles. The close-up images of the landing side are very different from the ones from the first touchdown side. We believe we're not looking at the bottom, but we're looking on the side of a boulder. And the features are very similar to the ones seen by Shiva. The colors are very uniform, and we see variations of the reflectivity at the 4% level. Further information is available on the poster session tomorrow that I encourage you to visit between 8 and to 12, where there is a poster by Schroeder et al. On ROLIS. Thank you very much.
Okay, the paper is open for questions. Andy? No, you can't, not you. You can't yell.
I was just noticing some of your pits, which are a few meter diameter. That would suggest that the mobile regolith layer is much deeper than the 10 or 20 centimeters that the other experiments were suggesting. Maybe on the order of a meter deep.
Yeah, I know, yeah.
I had a question about those as well. It looked to me more like they were mounds rather than pits. Can you tell that from the imaging? Is there a... Yeah, the dune field, right.
Yes, they're not mounts. They're really pits. I mean, we can see during the descent we have a rotation, and we have, although we were looking pretty much nadir, we have a slight tilt that enables us to do stereo, for example, from different images, so we can tell, and we can reconstruct a 3D model, and it tells us that they were really pits.
Okay, thanks.
So there were negative features.
I have two questions. Do you have an estimate of the albedo at the touchdown site 1 at the final landing site?
Not directly. This is something that Osiris can do much better because they have a much better calibration than we have. We were panchromatic. We are observing,
Okay. On the second question, could you explain your size distribution by a checking effect? For instance, on the surface of the asteroid, it has been proposed that the regolith could be formed by checking effect. Do you think that it's a possibility here for the surface of the comet?
Well, I think this is a possibility, of course, but it is also striking that we see the same distribution as the flying particles. So we need to find an explanation that can explain both.
Okay.